Hello, welcome to Maths with EJD. In this video, um I'll be starting a series or call that a playlist on graph and network theory. Graph and network theory. And the first video will be about introduction to graphs. I'm very sure when you hear the word graph, you're thinking of plotting X and Y axis and, plotting points on the coordinate system and joining lines together. In the case of graph theory, no, it's not that kind of graph we are talking about. Okay. So, of course, network will make more sense, right? Um, Network is more like you already know the idea of network, the connection between two or more entities, right? For instance, social media is a very good example of networks, right? You follow people and people follow you, depending on where you are. On Facebook, you have friends and friends have you, so to speak. That's network, right? And that's exactly what we are delving into. So, talking about graph and network theory now. Okay. So, um, okay. So this is more like graphs is more like the theory of this concept, right? While network is actually the application of graphs. Okay. Network talks about the application of that graph thing. Okay. I mean, this may be sounding somehow right now, but when we get into it, you'll get the gist. So I think it's good, just like you see, good to start with the basic concept of graphs. So introduction to graphs. Um, you need to know that graphs are fundamental. Graphs are fundamental structures. They are fundamental structures in discrete mathematics. In discrete mathematics and computer science. So you see, graph theory, network theory, very important in computer science because they talk about networking and things like that. So and they are used to model relationships, model relationships between objects. Okay. So graphs, right? Graphs consist of vertices. So graphs have vertices or what you call nodes, vertices or nodes, and they also have edges. Okay. Graphs have vertices or nodes or edges, which are actually connections. Edges are connections between vertices. Connections between vertices. Okay. That goes. Um, understanding, understanding the basics of graphs, the basics of graphs. Okay, there are types. You have graphs, types of graphs. There are types, and their representations, and their representations is critical for solving problems, for solving problems in various domains, such as networking. Just like I told you, you need the idea of graphs to do networks properly. So you have networking and every other place where you have networking applied, even in biology. So the network of proteins, for instance, networking biology, and even social sciences. So, I mean, this talks about interaction uh, that go on in society. So people are interconnected and they interact. So we need graph theory to decipher some of these things. So that's like the introduction, right, to graphs. Let me just call it that. Introduction to graphs. Introduction to introduction to graphs. So that's what this first video is about. Now let's talk about some definitions. We have some key definitions. For instance, I've mentioned vertices or nodes and also edges, which are which are connections between vertices, right? So now let's take some definitions that will drive home this whole point about graph. So for instance, let's start with the idea of graph. Now, what is a graph? So we say that a graph G, which is a collection of vertices and nodes, I mean vertices and edges. Okay, a graph, right, is a collection of a graph G, which is equal to VE, is a collection of vertices V. We have vertices V and edges E and edges E, where each edge, where each edge connects two vertices. Each edge connects two vertices. That is what a graph is. Okay. A very good example, like I mentioned before, okay, a very good example will be that in a social network, vertices, vertices can represent people. Okay. For instance, on Facebook, I am a vertex or I'm a vertex, right? And other friends that I have are also vertices. And the connections between us will be the edges, right? So in a social network, vertices can represent people, right? Vertices can represent people and edges. And edges can represent friendships. And edges can represent friendships. Okay. So, I mean, as we go deeper into this, you'll understand the whole concept. Okay, so that's the idea of graphs. A graph is basically a collection of vertices and edges. Okay. Um, so talking about vertices and edges now, vertices and edges. Of course, vertices is the plural of vertex. So vertices. So when we talk about vertices, right? The first one, let's talk about vertices. Vertices. So these are basically the points or nodes in the graph. They are the points or nodes in the graph. Those are vertices. Then we have edges. Edges. Just like we already know, they are the connections. They are the connections between pairs of vertices. And just like we're talking about social network, okay, I mean, we can give another example now. So what will be examples of vertices and edges? Okay. In a road network, cities are vertices, right? Cities are vertices. Cities are vertices, okay? And roads are edges, and roads are edges because those roads connect the cities. Okay. I mean, in the Nigerian context, right, we have key cities like Lagos, Abuja, Port Harcourt, right? So those are Lagos, Abuja, and Port Harcourt are vertices, but the roads that connect pairs of those cities or whatever, well, I mean, the roads, right, would actually be the edges. Okay. Now let's talk about directed versus undirected graphs. Directed versus undirected graphs. So, we are looking at the basic ideas for graphs. So let's talk about directed versus undirected graphs. Okay. Well, I think this should be a sort of intuitive, but let's look at it. Talking about directed graphs, they are also known as digraphs. Digraphs. Okay. So in this case, the edges have a direction. The edges have a direction. It reminds me of the idea of vector and scalar quantities. So edges have a direction represented as ordered pairs. Ordered pairs. Okay. That's like you have U, comma V. In this case now, so edges, I mean, directed graphs have edges that have a direction represented as ordered pairs. So the edges aren't just joining the vertices, right? They are actually following a particular direction. So let's look at an example, a practical example that is, imagine a Twitter follower, right? A follower, Twitter follower graph where U U goes to V, right? U goes to V simply means that U follows V. So Twitter is a very good example of directed graph. So U follows V. So because on Twitter, it's possible for you to follow someone and the person doesn't follow you. So that's a directed graph. So when you follow someone, that's a very good example. It's not the same as Facebook where if two of you connect, you have to be mutual friends. Of course, there's also the idea of following on Facebook these days, right? But for someone to be your friend on Facebook, it means you have both agreed to be friends. But on Twitter, that the only option you have is to follow someone or someone follows you. So you can follow someone and the person follows you. So those are like two directed graphs. But on Facebook, you are just friends. Okay? So that's directed graphs. And then we go to undirected graphs. Undirected graphs. Okay. Here, edges have no direction. Edges have no direction. Okay. Edges have no direction. And they are also represented. So these ones are represented as ordered pairs, right? But these ones are represented as sets. Represented as sets. So that's really important. That's, set UV. The other time it was ordered pair UV. Okay. Ordered pair UV. So it follows an order. But here they are just sets. So edges have no direction represented as sets UV. And like I said before, a very good example is the example of friendship on Facebook. Okay. So a Facebook friend graph, a Facebook friend graph where friendships are mutual. So on Facebook, you cannot be somebody's friend without the person be your friend. Friendship is mutual there. So friendships are mutual. But follows are not mutual, right? You can follow someone who doesn't follow you, and someone can follow you and you don't follow them. Okay. So, but friendship has to be mutual. So, and that is an undirected graph where the edges have no direction and they are represented as sets, and you see the set notation the way it is here. So set UV, whereas for directed graphs, right, you have ordered pairs UV because it's directional. Okay, so that's the idea of directed and undirected graphs. Now let's talk about special graphs, right? Um, let's go to talk about the idea of special graphs. Well, I can call, okay, I mean, let me just start a whole thing, special graphs. So we have some special graphs. Um, so the first kind of graph that is special is what we can call a complete graph. Complete graph. When do you say that a graph is complete? So in this case, right, every pair, every pair of vertices, every pair of vertices is connected by an edge. Okay. Every pair of vertices is connected by an edge. So it simply means that imagine that you have A and you have B and you have C. So if we connect AB and we connect AC, that will not be a complete graph because by essence, a complete graph actually has a complete graph has all the pair of vertices are connected. So in this case now, A and C are not connected. But by the time I connect A and C, then that becomes a complete graph. So every vertex is connected to another, every pair, every possible pair. So in this case now, the pairs will be A, B, AC, and BC, and they're all connected like this. So that is the idea of a complete graph. So other ideas will be the notation, right? The notation the notation for a complete graph is this. The notation is Kn, where n is the number of vertices, where n is the number of vertices. So that means this is a K3 complete graph. This is a K3 complete graph because all the possible pairs of the three vertices are connected by an edge. So a very good example of that would be uh, a network, a network where every computer, where every computer, where every computer is directly connected, is directly connected to every other computer, to every other computer. Okay, just like what I have here. So if this is computer A and this is computer B and this is computer C. So A is connected to B, A is connected to C is connected to A, C is connected to B is connected to A, B is connected to C. So that's the idea of a complete graph. Okay. Now let's go on to talk about bipartite graph. Bipartite graph. That's the second kind of special graph. Two, bipartite graph. Okay. So for bipartite graph, we have here that the vertices can be divided, the vertices can be divided into two disjoint sets, U and V, such that every edge connects a vertex, in U to a vertex in V. Okay. So that's vertices can be divided into two disjoint sets, U and V, such that every edge connects a vertex in U to a vertex in V. Now, a very good example of that would be this. A very good example of that is a job assignment graph. So you're assigning jobs to people. A job assignment graph where one set represents jobs, one set represents jobs, one set represents jobs, and the other represents workers. Okay. I mean, that's very imaginable. It's a bipartite graph. So a very good example of that would be something like this. You have okay, we're talking about jobs and workers, right? Imagine that you have job one, you have job two, or better still, yeah, here we said U and V, right? So you could as well just say this is U1, this is okay. I mean, let me use the idea of U1 and U2. We are going to have ample opportunities to talk about all of these things. Okay. Um, Imagine that you have job one and you have job two, and then you have we're assigning jobs to workers, and this is worker one, and this is or better still, this is a worker, right? This is worker, so this is worker one, and this is worker two. So And for a bipartite graph, right, U1 is joined to V1, where and U2 is joined to V2. That's the idea of a bipartite graph. Okay. Of course, this, okay, I think this to drive the point home actually, right? You have U1. So this is one subset, and this is another one. Okay. Okay, maybe I think it's better to do it this way because from the very definition, right, vertices can be divided into two disjoint subsets U and V, such that every edge connects a vertex in U to a vertex in V. So this is one subset of the graph. This is one subset of the graph, and this is another subset. Okay, and then just one edge from each subset is connected to another edge. I mean, another one edge connects two different vertices in the other sets. So you can have U1 connecting V1 and then U2 connecting V2, something like this. That is what we call a bipartite graph. Okay. Now we have another special type of graph, which is called a tree. So we can have a tree. So you can already begin to imagine what a tree might look like. Let's see. So you have a tree. So number three, a special graph called tree. Okay. So here, um, this is an it is a tree is an acyclic. It's an acyclic. It's an acyclic connected graph. Acyclic connected graph with n vertices, with n vertices and n minus one edges. Okay. So a very good example, of course, that might look abstract, but you're going to have examples. So a good example of this would simply be a family tree, a family tree, or a hierarchical file system, a hierarchical file system. Okay, a hierarchical file system. So let's see an example of a tree. So let's look at a tree graph. Imagine this. You have you have so imagine that you have something like this. So this is connected to this is connected to this. So this is one, this is 0, 1, 2, and this is 3, 4. Okay. So this is actually a tree graph. So it's actually is an acyclical connected graph with n vertices and n minus one edges. So you have five vertices and four edges, right? So just like the definition says, right here you have five vertices, five vertices, and four edges, as you can see. Five vertices, four edges. That is what a tree looks like, something like this. So just like a family tree or a hierarchical file system, that is a very good example of a tree. So let's talk about the next thing. Um, and that is called a cycle. Here we came up, we have the idea of acyclic. Like as you're going to see very soon, a cycle simply is exactly like a closed loop. That you get into that system and you're trapped. That's the idea of a cycle. So let's look at that. So, and it's a special kind of graph called a cycle. A cycle. So a cycle is actually a graph that forms a closed loop. It's a graph that forms a closed loop. It forms a closed loop with no repeated edges. Forms a closed loop with no repeated edges or vertices. no repeated edges of vertices, except the starting and ending vertex. No repeated edges of vertices, except except the starting, starting and ending vertex. Okay, so it ends with what it starts with. That's basically what this idea is. So for instance, we have the example, we have this example of a circular racetrack, a circular race track. Okay, that would be like a circle. That would be like, yeah, that's a cycle. Or in fact, it can even be a rectangular racetrack. You start from where you stopped. Okay, that is what a cycle looks like. Um, just like I was saying, you could actually be talking about. So imagine uh you have one, or let's start from zero, one, two, three, like this, and then you have something like this. So this is actually a cycle. So the path is closed. So you cannot get out of this loop. So it's closed. Okay. There's no exit. So you can just keep moving around and round. That's why it's called a cycle. A cycle. All right. So let's go on to talk about, I think we are done with special graphs now. We are done with special graphs. Now, the next thing I like to talk about would be representation of graphs. Representation of graphs. So let's talk about representation of graphs. Um, oh, okay. No, this doesn't work. Okay. Representation, representation of graphs. Okay. Graphs are actually represented in three key ways. Three key ways. And the first way is that we can represent graphs using adjacency list. Adjacency list. And what that simply means is that each vertex, each vertex or node stores a list of adjacent vertices, a list of adjacent vertices. Okay, more like every vertex it is connected to. Then this is actually efficient. It is efficient for sparse graphs. That is, I mean, graphs you have under control. Graphs that are not so dense, so to speak. Not plenty, basically. Efficient for sparse graphs. So imagine this example. Imagine this example uh that you have I'm trying to see. Okay. Um Okay, let me just give the example, then probably I'll try to draw that out and see how that goes. So if you can represent a graph by using its adjacency list. So imagine there's a node A and the adjacent, I mean, yeah, node is vertex, right? There's a vertex A and the adjacent vertices are B and C. Then B also has adjacent vertices AD. Then you have C with adjacent vertices AD again. Okay. And then you have D. You have D with adjacent vertices BC. Okay. Adjacent vertices BC. So this represents a graph with edges, a collection of edges AB, AC, BD, and CD. That's what this graph represents. So we can try to draw that. And if we try to make that out, that'll be something like this. Okay. So let's say you have A. So A is connected to A is connected to B. A is also connected to C. Okay. And then next, you have B, which is connected to D. So let's say this is D. So B is connected to D. And then you have C, which is connected to D. So um, adjacency list is a very good way of representing graphs. So you just pick this A now. So if you pick this A, you see it's connected to B and C like that. And then you pick B. If you pick B, B is connected to A and D, just like what you have here. If you pick C, C is connected to A and D, like what we have. And if you pick D, D is connected to B and C. And that is exactly what we have here. So you can represent a graph using adjacency list, like that. So that's one way to represent a graph. Okay, so let's talk about another way of representation, and that is what you can call, I think it's degeneracy. Sorry, you can call it adjacency matrix. Sorry. Um, Second way of representing a graph will be by adjacency matrix. So we have adjacency list, now adjacency matrix. Okay. So for adjacency matrix, basically, all we have is that we have a n by n matrix M. It's an n by n. I mean, I think it should be like an n by n matrix M, okay, where Mij is equal to 1. If there is an edge, if there's an edge between vertex I and J, and 0 otherwise. Of course, that may be like some abstraction, but the beautiful thing about graphs is that even if it's looking like it's not clear, you can easily get an example to clear your doubts. I mean, but this is basic, right? An n by n matrix M, where Mij means I and J means elements that are not of the same row and column. Maybe like definitely not 1 1, not 2 2, not 3 3, not 4 4. If it's a 4 by 4 matrix, but if it is 1 2, 1 3, 1 4, 2 1, 2 1, 2 3, 2 4, or 3 1, 3 2, 3 4. I mean, you keep skipping all the IIs or the JJs, right? So all the IJs are not one, right? All the IJs are actually one if there is an edge between vertex I and J. Okay, so if we have okay, I mean, instead of telling plenty stories, let me just give an example to drive the point home, right? So imagine this example that we have, we're talking about adjacency matrix. So imagine this, you have 0 1 1 0, and then you have 1 0 0 1, and you have 0, I mean 1 0 0 1. Then again you have 1 0 0 1, and then you also have 0 1 1 0. So this is an adjacency matrix. This is your matrix M, and this actually represents the same graph as above, the same graph as above. I mean, that's graph ABCD. This is what it represents. This actually represents it. So let's look at the connection. So imagine this is like okay, this is A, B, C, D, and this is A, B, C, D. So if there's a connection between, of course, A and A, we are talking about IJs, right? So A and A will be 0, B and B is 0, C and C is 0, D and D is 0. So all those ones are out of it. Like what I mean is all of these guys are out because they are not IJ, they are II or JJ if you like. They are the same number of rows, not row column. So 1 1 2 2 3 3 4 4. Those ones are out. So they are all zeros. But if there's a connection, so there's a connection between A and B. As you can see here, there's a connection between A and B. So that will be 1. There's a connection between A and C, that's 1. Between A and D, there's no connection. So if you had this kind of connection, then there'll be 1 there. So you see between A and D, it's 0. Okay. Between B and B is BA. So if there's AB, then there's automatically BA. Then there's a connection between A and C. Okay. So if there's a connection between A and C, this connection now. So if there's a connection between A and C, that means one. Okay. So AC is one. Automatically CA is also one. So between BC is zero, right? There's no connection between B and C. This connection doesn't exist. So if you drill before, so between B and C, it's also zero. Of course, automatically BC zero means CB is also zero. Then there's a connection between BD and BC. So you can actually so the same graph you have represented using adjacency list can also actually be represented using adjacency matrix. Okay. Um, well, it all depends on the situation for using each type actually is dependent on your particular scenario, right? I mean, it will look like the adjacency list is more intuitive than this one. Okay. So we have adjacency list, adjacency, or is it called adjacency? Adjacency list, adjacency matrix. And then the third way of representing graphs would be the incidence matrix. Incidence matrix. So incidence matrix. That's the third way of representing graphs. Incidence matrix. Okay. So here you have an n by m matrix. It's an n by n matrix I, where n is the where n is the number of vertices, and m is the number of edges. M is the number of edges. So here I row with I rows and j columns is actually one the vertex, if the vertex I is incident, if the vertex I is incident to edge j, is incident to edge j, and zero otherwise. So a very good example of this would be this example now. We have this example uh for a graph with vertices A, B, C, D, and edges edges. Say edge E1 is AB, edge E2 is AC, okay, edge E3 is BD, and edge E4 is CD. Okay. How do you represent that? So we say for a graph with vertices A, B, C, D. So don't forget, if vertex I is incident to edge J, that IIJ will be one, otherwise it will be zero. Now look at this now. So this is what this is basically about. You have okay, say, or better still, let me just do this. A, B, C, D, right? A, B, C, D. So we have edge AB, we have edge AC, we have edge BD, and we have edge CD. Okay, I mean, just like what we had before. So, but here we're talking about incidence, right? So here this is like 1, 1, 0, 0, 1, 0, 1, 0, and then this is 0, 1, 0, 1, and this is 0, 0, 1, 1. Okay. And what is basically happening there is that okay. So what I mean, see, this is A, B, C, D. Let's make sense of this. A, B, C, D. So what is that? What exactly is happening here? AA is giving you one. What that simply means is that for IIJ, that means the row and column are not the same. IIJ will be one if vertex I is incident to edge J. Okay. So vertex I is incident to edge J. So edge AB now. This is edge AB and vertex A. So now this is now represented like this. Now you have 1, 1, 0, 0, BA. Because we have AB, so you have AB, this is B here, and then this is BC, and that goes on like that. So that's the idea of the incidence matrix, an N by M matrix. So you have number of vertices. There are 4 vertices here and 4 edges too, interestingly. So 4 vertices and 4 edges. All right. Um, So if the vertex I is incident to edge J and and 0 otherwise. So the vertex I is incident to edge J. We have IIJ to be 1. So like here now, we still have some values of 1 along the what in matrix we would call the principal diagonal, which would be like all the 1, 1, 1, all the 1, 1, 1, 2, and all that. So that is the incidence. So this is different from where we're coming from. That if there's a joint, if you have a joining between between 2 vertices, then that value will be 1. All right. So so from all we've seen so far, you see that graphs provide a versatile framework for modeling and solving real-world problems, and each representation and type has unique benefits depending on the problem's requirement, whether it's for memory efficiency, transversal speed, or visualization simplicity. So, so from there we can actually draw some kind of inference, right? That each representation, representation each representation has a unique benefit. That's a unique benefit. Each representation unique has unique benefits depending on the problem's requirements, whatever problem we are solving, on the problem's requirements. And that can actually be something like you're talking about memory efficiency. Do you want to maximize memory? Then it can also be for maybe transversal speed, depending on what you're working on, transversal speed. And then it could be for visualization simplicity. Okay. So depending on the situation in which you are, you can choose what you do want and what you don't want. All right. So that we've come to the end of this. In the next video, I'll be showing you. Interestingly, Python, there's a Python library called Network X, Network X, which is used for visualizing graphs and networks. Okay, so in the next video, I'll be showing you some of these things I've discussed here, and I'll be showing you the Python code to plot, to represent those graphs, right? So if you have not subscribed to this channel, be sure to do that right away, and hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if you want me to solve a problem or teach a topic. Then like and share so that more people can have access to this great learning. Till I come your way again. Um, keep connecting networks, right? Bye.